Stephanie. Welcome, architecture students, to Module 10. You've been studying for 9 weeks about engineering design. Today's your 10th week, and we're going to be talking about electrical engineering basics. I'm Scott Brown. I work at a building design firm called Arup. Once you graduate, you'll probably be doing a lot of work with me. So over the next 3 hours, we're going to be focusing on the basic theory of electrical engineering, some of the applications, as well as how to apply this to building design. Of course, tonight we don't have 3 hours, we have 10 minutes, so we're just going to be focusing on the definitions and the core fundamental equations of electrical engineering. So let's just jump right into it. The first property of electricity that we really need to talk about is voltage. So what is electricity? All right, voltage is the difference in electrical potential energy from one point to another. And I know that's just a bunch of words to you right now, but consider what potential energy is. Potential energy is the embodied energy of a system due to its configuration. Consider a man standing on top of a building. There's not much going on right now, but he has a lot of potential energy. Gravity is exerting this force on him, trying to pull him down. And if we were just to create a path of motion, then that potential energy would immediately get converted into kinetic energy, to his dismay. It works very similarly with electricity. In a battery, you have one side of the battery that's stored with positively charged ions, and the other side is stored with negatively charged electrons. They want so badly just to come together. There's a magnetic attraction between them, and the electrons and the positively charged ions want, there's a force bringing them towards each other, but they can't move. So that desire for them to move towards each other is the voltage. Now, again, if we were simply to create a path of motion, then that potential energy could get converted into kinetic energy. The electrons would be able to run along this wire towards the protons, into their loving arms. And that conversion of the electrical potential energy, the voltage, into kinetic energy, the flow of electrons, the kinetic energy is called current. Current is the flow of electrons per unit time. It's the number of electrons moving through a wire per second. And that's the energy that is transferred that begins to do the electrical work that you want it to. Now the wire can either conduct this current very easily, or it can be very reluctant. And so the wire has a third fundamental electrical property, and that property is called resistance. Resistance is the opposition to the flow of electrical current. So some chemicals are very conductive, some do not like current flowing through them, and so they slow the current down. Does anybody know what the most conductive chemical element is?
Gold.
Best conductor, gold. It's a good answer. It's not right. Silver is actually a little bit more conductive. We use copper in our buildings because silver is just so damn expensive. Sometimes we use aluminum because it's pretty good too. These are the resistivity values. So you can see times 10 to the negative 8, this is like 0.00000000282. They're very low values for the best conductors because they have a low resistance. So there's little opposition to the current flow. The values, the chemicals with very high values, glass, wood, and air, they're good insulators because they do resist. Current does not want to flow through air or glass. So if you put an air gap or cover something with glass, the electricity is not going to move through there. So that makes a good insulator, a good barrier to prevent electricity from moving places. Resistivity is also a measure of cross-section as well as the type of material. Consider water flowing through a pipe. If you want a lot of water going through there and you have a very small pipe, you're going to have a hard time getting the water to move as fast as you want it to. So you need to make the pipe bigger and bigger. It's the same way with wire. If you have a very small wire, you're not going to be able to get a lot of electricity going through there without having the wire melt. So you need to make the gauge larger and larger in order to decrease resistivity and to make the current flow faster. So sometimes wire isn't even enough. If you need so much electricity, say you're moving current from the bottom of a skyscraper all the way to the top and there's a lot of it, we use this thing called bus bar, which is just a bunch of copper plates bolted together because we need so much electricity going through there. So we have voltage, which is the potential energy difference, the magnetic force between electrons and positively charged ions. We have current, the flow of those electrons around a circuit, and resistivity, opposition to that flow. So how do these things actually work together in electrical engineering? Well, first we create a circuit. So we have a battery here with a certain voltage that's denoted with a V. It's inducing a current around the circuit because there is a connected path there, and the current is denoted with an I. If that's confusing, blame the French. And we have a dimmer and a light switch, with both have an associated resistance. They're resisting the current to some degree. Now the dimmer's job is that it can change its resistance. So the dimmer can become more resistant or less resistant. And as it becomes more resistant, the current in the circuit goes down and the light dims. That's how it works. They're related by this fundamental equation, V equals I times R. It's called Ohm's law. Another fundamental equation is the equation for power, which is another derivation of Ohm's law. Power is the rate at which electrical energy is transferred. If you're operating a washing machine or a blender or some sort of application, it's going to dissipate a certain amount of power. It needs a certain amount of electrical energy per unit time in order to operate effectively. And that energy is measured in power as current times voltage, I times V. It's another equation. So here's just a chart of some of the basic appliances you might use in a building and how much power they might consume. A hair dryer consumes about 1,000 watts of power, which is much more than, say, like a little blender would consume. So just as an example, let's say we have a 5,000 watt dryer. That dryer is going to be 5,000 watts no matter what. No matter what voltage you assign to it, it's always going to require that same amount of power to operate. Let's say in our building, we give it 208 volts. We supply the voltage, the dryer has an assigned unit of power, and we can use this equation, I equals P divided by V, to figure out what the current is. It's going to be, in this case, 24 amps. If we were to assign a different voltage to it, like say 120 volts, then the current might be a different current. In this case, it would be 41 amps. So you can see how we can, as electrical engineers, change the voltage in order to manipulate the current. That can be very useful in electrical engineering. The funny thing about these equations, there's 2 equations and only 3 variables. So by substituting, we can actually create a series of 12 equations. If you have any of these 2 variables, power and resistance, or voltage and power, or resistance and current, if you just have 2 of them, you can use these equations to get the other 2. It's very useful. If you don't have this chart on you, you can always remember the words that Ohm's dying Uncle Ben told him. With great power comes great resistance squared times current. So in summary, the fundamentals of electrical engineering. The first fundamental property of electricity is voltage. That's the potential energy difference between 2 points. Like a man standing on a building, there's a great potential for the energy to come into reality. There's current, which is the actual kinetic energy flowing through the circuit, measured by the number of electrons moving per second. There is resistance, the opposition to that current flow, based on the material and its cross-sectional area, how big it is. And then there's power, the electrical energy transferred per second, which in building applications is the power required to run certain types of devices. And they're all fundamentally related to each other by these 12 equations. So, thank you for bearing with the introductory section of our electrical engineering course. Next time we'll be talking about alternating current and 3-phase power. I know you're all really excited about that. Thank you so much.